This video is going to be on the least squares method for linear regressions, so we're going to derive the formulae for this method. So firstly, let's discuss what the problem is. So the whole idea of linear regression is that you're going to have a collection of data points where these data points are going to have two real numbers, and these data points are going to seem to be linearly related. When you plot them on a graph, the relationship between the two real numbers that make them up appears to be linearly related. And then the whole idea of linear regression is to find a straight line that best summarizes your data, that is the best fit for your data. So just drawing a picture of this. So we've got a portion of the plane here. So our data points are going to lie in the plane as they consist of two real numbers. And so we might have them plotted on like this. So here are some data points. So each one of these represents a point. So there I've got 7. So each one of them will consist of two real numbers, an x coordinate and a y coordinate, or an x value and a y value. And we'd have 7 of these, so it would go up to x7, y7. More generally, we might have from the first one up to the nth one, xn, yn. And then you can see that these points don't lie on a perfect straight line. If they laid on a perfect straight line, then it would be more easy. You just have to find the equation for the straight line connecting two of them, and then it would go through all the others. However, in this case, the idea in linear regression is that they're not going to perfectly lie on one straight line. However, you can see that it does look as though they have a linear relationship. The y and the x term are linearly related. You should be able to write y as a linear function of x. So what we now want to do is find what I'm drawing here in red, the sort of line that's down the middle that is the best sort of fit for them. And we'll have to quantify what we mean by best fit. Intuitively, this is what it means on the picture, the sort of line that sort of best summarizes it, so that you've got sort of as much of them above the line as you've got below the line, so that the line is sort of in the middle and nicely summarizes them. So that, for instance, if you consider this, for instance, some sort of function that links one value to another value, then you might like to know, given that we've got this initial data set that we've got from experiment, say for instance I was to now get an x value of this, so x8 here, what can you predict what y value will accompany that x value? And if we had this, the equation of this line, we'd just be able to plug that x8 into that equation and get a y value out. So that's the idea of what we want to do in linear regression. We want to find a straight line, the best fit straight line to summarize a bunch of data, so that we could then use that to make predictions given another x value, what y value we could expect. So let's have a think about how we might do this then. So we'll say that we've got n points, x1, y1, all the way up to xn, yn, and we now want to try and find this best fit straight line for those endpoints. So a straight line is going to have equation y is equal to mx plus c. Now in our picture, of course, the best fit line seems to have intercept 0, so c would have been 0 in that case, but in general I can easily draw a picture where the best fit line wouldn't go through 0. So here's some data points where quite clearly the best fit line would be something like that, and the intercept wouldn't be 0. So in general, our equation is going to be of this form. So we just need to try and find what is the best m and the best c for these data points. So the first thing to say is that there is no best way of doing this, because this whole concept of what is the best fit, how do you make that formal? What does that mean? all that means at the moment is our eyes like the look of this line that's going in between these data points, but how are we actually going to make that formal? Well, we're going to actually have to define what we mean by best fit, and there are loads of different ways that you could define this, and we're actually going to take the least squares approach to this because it's a good concept of best fit, and it's actually computationally beautiful, computationally tractable. But I firstly just want to give some other ideas of what we could do to try and find this best line, and then sort of discuss why we're not going to take those approaches, because initially these ones that we're going to discuss might be more intuitive things to do. So just to draw a bigger picture then, with the actual pen rather than the pointer. So we're just going to have a zoomed in picture. So we'll just take 3 data points initially, just for simplicity, and we'll put a best fit line, something like that. So one thing we could do is we could say that the vertical distance between the points and the equivalent point of the line, I'll just show on this picture what I mean by that. So each of these 3 points has an x value, so we'll just call that x1, that x2, and that x3, and then they have a y value as well. Now, their y value is not equal to the y value that the line would have predicted. So for this x1, here is the y value that the equation of the line would have predicted, and here is its actual y value. And similarly for these ones, their y values differ. So what we could do is look at this difference between all of the y values, and we could say that we want that to sum to 0, i.e. there are a bunch of data points that are above the line, and there are a bunch of data points that are below the line, and we want the amount, when you sum up all of the ones that are above the line, how much they're above by, to equal the amount by which all the ones that are below the line are below it. Now in this picture it isn't actually true, because you can see if I add that to that, it's not equal to the size of this one, so we'd actually have more positive than negative. But that is an approach we could think about doing, because it's a fairly intuitive concept of how we want this line to best fit our data points. So we could think about doing that. We could think about trying to, I'll go back to white because red won't show up properly. We could think about trying to sum up, and initially I will write for these sums I is equal to 1 to n. However, we're going to do so many sums from I is equal to 1 to n in here that I'm actually going to drop this very quickly and just put summation, and we'll have this understanding that whenever you see a summation sign, it means over all the i's. So we could try and do the yi minus the predicted, which would be mxi plus c. We could sum this up and we could say we want this to equal 0, and I want you to find me m's and c's that make this work. That seems like a fairly good idea. If you could find me an m and a c, then that might be a good fit. Let me show you why that's not a good idea. The problem is that you can see from this equation, all your yi's and your xi's, they're all just constants. So you're just going to end up with a huge, great equation with just 2 variables, an m and a c. In fact, we could change this. So just doing this, we can split this into the sum over yi's, and I'm dropping the from I is equal to 1 to n. And then we'll just have minus m sum over the xi's, and then we'll also have a minus c summed over all i's, which will just become minus cn is equal to 0. So this is a constant, this is a constant, this is a constant. So you've just got an equation in m and c, and you can see that you've got one equation, 2 variables. There isn't just one solution to that, there's a whole bunch of solutions. And even though amongst that whole line of solutions, I could plot this on a plane, we could consider the plane where we have m here and c here. There's going to be a whole line in that plane of solutions that satisfy this equation. There is somewhere amongst that line a perfect solution that is the one that we intuitively want. However, we're not going to actually be able to find that. And let me show you how bad all of the other solutions on that line are potentially going to be. So we could actually take 3 data points that are actually on a straight line. So let's say they all have y equal to some constant, so we might say 2. So they're all on this straight line, y is equal to 2. So quite clearly we know what the best fit line would be intuitively. It's the line, y is equal to 2. However, this approach would quite happily give you that line as a line of best fit, because it would also satisfy this relationship, because I've made it go through that middle one, and then I've angled it such that, positioned it such that the amount that this one is above is the same as the amount that this one is below, so that those sum to 0. So that would also satisfy that property. And you can think about all the other lines, just changing the angle of this, that would also satisfy this equation. So all of those are going to come out as solutions. So that is why this is not a good approach to take, because it gives you this whole range of solutions, and how are you supposed to find the one that actually is the intuitive best fit? So that's not the approach we're going to take. Next idea is, so the problem was that we were looking at just the difference between the actual value and the predicted value by the straight line. And the positives could cancel with the negatives so that it would overall give 0. So why don't we instead take absolute values of these differences and then just find the m and the c that minimize the sum of the sum of all those absolute differences. So we could next consider doing this: sum over all I of the absolute value of yi minus mxi plus c. So what that means is, for every single data point, look at the difference between the actual y value and the predicted y value, which is this, and take the absolute size of that. So all of these ones that are below, they will now become positive numbers. So this will be a great big sum of positive values, so you will get a positive value at the end. It will always be non-negative. The lowest it could ever be is 0 if, by some miracle, all the points do lie on a perfect straight line. And then you could ask, find the m and the c that make this a minimum. That's a brilliant thing to do. Absolutely brilliant. However, the problem is, how are you actually going to find the m and the c that make this a minimum? Absolute value functions are quite difficult. This thing that you're going to get here isn't going to be simple either. It's going to have loads of separate absolute value signs. So you're going to have, if we write a little bit of this out, it's going to become y1 minus mx1 plus c plus the absolute value of y2 minus mx2 plus c plus, and then it will go all the way up to yn minus mxn plus c. So we can think of this, we can call this s for sum, and then it's a function of 2 real variables. So we could plot even a 3-dimensional graph for this. So we could imagine having s here, and then we can have mc here, and we can work out what the value of s will be for all the different values of m and c in the 2-dimensional plane, and we can plot them here. And it's always going to be a positive value, so the function is always going to be, it's going to be some surface that's above the s is equal to 0 plane here. And then we could try and work out where the minimum is. The problem is that this function is not nice. How are you going to actually find where the minimum of that function is to find your m and c? The reason it's not nice is because of these absolute value signs, which mean that the classical way, the beautiful way that we have of finding minima, which is points where the derivative, both partial derivatives in the m and the c direction, are equal to 0, so that it's a true stationary point or turning point, that's not going to work here, because absolute values have places where they're not differentiable. And we were not just dealing with one absolute value, that's the other problem. If it was just a single absolute value, then, if I show you something, so if we have the function y is equal to mod of x, simple absolute value, then we know immediately where the minimum of that is. It's at x is equal to 0. We might not be able to differentiate it there and show that the derivative is equal to 0, but we still know something about this function, and we can find its minimum. In the multivariate world, we could imagine a function s is equal to mod m plus mod c. So, little three-dimensional graph. So again, s is the vertical axis, m is here, c is here. What does this look like? So in both of the planes, so if you consider when c is equal to 0, it's just going to be mod of m, so it's going to look like this. And then if you consider when m is equal to 0, again it's going to look exactly the same. So something like that. And the picture's getting quite confusing, but it's the surface that sort of looks like that. It's if you imagine connecting, so here we have this line in the m is equal to 0 plane, and we have this line in the c is equal to 0 plane. If you imagine putting a plane through them, that's what it's going to be in this first quadrant of the domain up here. Then in this quadrant of the domain over here, the second quadrant, you've got this bit, this line here, which is in the m is equal to 0 plane, and then you had a line that's very difficult to see now that was in the c is equal to 0 plane going backwards this way. And again, you want a plane that goes down there and goes through both of them, and so on. You can hopefully appreciate that it's this thing that's got rotational symmetry. If you rotate it round by 90 degrees, it rotates onto itself nicely. It's rotationally symmetric. So again, here, even though you can't differentiate it, you can see where the minimum is. It's at m is equal to 0 and c is equal to 0. So we can sometimes make absolute values tractable for finding minima. However, look at what we've got here. This is an absolute nightmare of a function in m and c. How are you going to work out where the minimum of this is equal to? So it's not nice at all. Difficult problem. So that's the reason we're not going to do that, although that is a very credible way of talking about best fit. What we are going to do instead is the next thing up, which is the idea of least squares best fit. And the brilliance of this is suddenly finding the minimum becomes easy using calculus, because we're not dealing with absolute value functions. So we are going to consider trying to minimize this sum instead, which is the square of those differences. We will look at yi minus mxi plus c squared. So that is all of these differences between the real y values and the predicted y values, which are these. And then instead of taking the absolute value, you now square them. Now the brilliance of squaring them is all the negative ones will become positive values. So it gets rid of the problem that we had initially of negatives cancelling with positives. And the other brilliant fact of squaring, unlike the absolute value sign, this thing, we're going to be able to find its minimum just by differentiating it, whereas we can't do that in this case. Now, so far I have presented this as a compromise. I've said really we want the m and the c that minimises this, however we can't have that. So the next best thing is to find the m and the c that minimises this, and that's the best we can do. However, that's not fair to this. This whole problem of finding the best fit line for these data points, what is meant by best fit? Nowhere is it God-given that this is what is meant by best fit. It's not written in stone that this is what is meant by best fit. Yes, when we think about it, this seems like a very credible idea for what is going to be the best fit. However, really, we're looking for a line that visually is satisfying for our eyes. And it isn't written in stone that this one is going to give the line that is most visually satisfying for our eyes. How are you ever going to prove that? So actually, this one is a credible alternative, a credible separate definition of what is meant by best fit. It might be the case that actually the line that this one gives is more visually pleasing than this one. And let me just give you a little more insight into that. When we square these differences, let's think about what's going to happen to the size of them. So if we imagine firstly positive numbers, so let's say a is greater than 1, so a is just representing a number now, but we can think of it as these differences here. If those differences are greater than 1, then they're going to become bigger. So a squared is going to be bigger than a. So an example would be 2, for instance. 2 squared is 4, so they get bigger if they're bigger than 1. In contrast, if a was less than 1, then a squared is actually smaller than a. So if you think about a half, that's less than 1. If you square that, it goes to a quarter, so it actually shrinks down in size if it's less than 1. More generally, we can put absolute values around there. So absolute value of a is greater than 1 and absolute value of a is less than 1. And we can put absolute values here as well. And the rule holds true. So for negative numbers, when their modulus is greater than 1, then when you square them, that thing is now going to have size greater than the modulus of a. So negative 2, when you square it, it goes to 4, and that has size greater than the absolute value of negative 2, which is 2. And the same happens for those small negative numbers, so minus a half. If you square it, it will go to a quarter, and that thing's size is smaller than the size of the original negative number. So what does this mean in terms of this sum? So remember, we are going to find m and c that minimises this sum. It means that if this line has points that are far away from it, a distance away from it greater than 1, so if this distance between the point and the line is greater than 1, then that's going to be magnified in this sum. Whereas if the difference is actually only very small, less than 1, then that's going to be shrunk down in this sum. So what this sum is actually doing is it's exaggerating differences that are bigger than 1 and shrinking differences that are smaller than 1. And then we're trying to minimize that sum. So actually, it's saying pay more attention, put more weight on points that are quite far away from the line. It's putting more weight on those points than this sum would do. So in a way, it's actually discouraging points from being further away from the line more so than this one. So it's not actually necessarily a bad definition of what is the best fit. So overall, what I hope I've communicated to you is there is no God-given, written in stone definition for which one is going to be the best fit. The M and the C that minimise this is going to be a good line that is going to be visually pleasing to us, potentially even more visually pleasing than the one that would come from this. So this would yield an answer. The answer might not be tractable to us, but or at least we might not be able to derive a beautiful formula for it in the way that we can for this one. But if you gave me an x1, some data points, say my original 7 data points, x1, y1 all the way up to x7, y7, then I could in principle find you the m and the c using this method and find the line that minimises this sum. I could then also find you the line through this method, the m and the c that minimise this sum, and we could compare them and we could see which one is actually more visually pleasing. And it isn't necessarily true that this one will be more visually pleasing than this one. So this is actually a credible definition for what is meant by best fit, because we're making it up, because there is no God-given answer. So this is the whole ethos of least squares linear regression. You find the m and the c that minimise this sum, and that's your best fit straight line. That's your least squares best fit. called least squares because it minimises the squares of the differences of the points, the vertical differences of the points to the straight line. So the brilliant thing about using least squares best fit is that this is actually tractable. It's possible from this to actually get a formula for what m and c need to be in order to minimise this in terms of all the xi's and the yi's, and that's what we're now going to derive. So I'll just copy out. We are trying to minimise this sum, which is the sum of these vertical differences, so yi minus mxi plus c squared. So I'm going to draw a little picture here. So the way we're going to do this is we're going to say that at a minimum, the derivatives, both partial derivatives, are going to have to equal 0. And we're going to find that there's only one place where both partial derivatives are equal to 0 for this function, and that therefore has to be our minimum. Before I do that, I just want to convince you that that's the right thing to do, that the place where this function is going to be minimized is the place where both partial derivatives are equal to 0. So this is a function of m and c, and it spits out an s value. So that's the first place that where this formula looks extremely confusing, because it's very tempting to think that the x and the y are our variables here. They're not. Those are the things that we were given in the problem. We were given all the points x1, y1, x2, y2, all the way up to xn, yn. Those are just constants. The variables here are the m and the c. Those are the things that we have the power to change, and they can take on any real number. So we have the whole R2 plane as our domain here, and then the answer is going to be a real number 2. It's this s value, and we want to know which m and c should we pick to minimize this. So where is this surface, this s surface at a minimum? So the reason I've only drawn the positive part of the graph, the reason I haven't got this negative part down here, is because the value of this function is always going to be non-negative. At the very smallest, it will be 0, which is where all of these vertical differences are equal to 0. But because we're adding up loads of square numbers, it's never going to be a negative number. So it's always going to be non-negative. So whatever this surface looks like, it's always non-negative. Now, let's try and get a little bit more intuition for this by actually expanding this out. And unfortunately, when we do expand this out, it temporarily looks even worse. However, I think it is important to do this just to nail into your minds that the m and the c are the variables here. So I want to rewrite this in a form where it makes it obvious that the m and the c are the variables. So let's take it down here. So we firstly need to expand out that square then. So we're going to get yi squared, and then we'll get minus 2 yi times mxi plus c. And then we're going to get plus mxi plus c squared. So let's try and expand that out in one go. So we'll get plus m squared xi squared plus 2mxi c plus c squared. So hopefully I haven't made any mistakes there. And now I want to separate this up and rewrite it so that it's written in a form that makes it very obvious that the m and the c are the variables. So this first bit is not a variable in m or c, it's just a constant. So we'll just have it as sum of yi squared on its own. Then this next bit here has an m, it's the only variable. The other two bits are not variables, so we'll have minus m times, then its constant, its coefficient, is going to be, well, we can take the 2 here, I think it will look better, times this yi xi. So I've pulled the m out of the sum as well. So we're doing quite a lot here. We're splitting this sum into how many different pieces are there going to be? 1, 2, 3, 4, 5, 6. We're going to split it into 6 different pieces. So here's the first bit, and then here's the second bit. It's still just a sum over I. Remember, we've already agreed that we're dropping the I is equal to 1 to n because it would just be painful. And then we've pulled the m out because as far as the sum is concerned, the m is just a constant. So we work out this great big sum, we multiply all the xi's by the yi's, or by their corresponding yi's. Note that this is just a sum from I is equal to 1, to n, so it's not a double sum. So it's x1 times y1, x2 times y2, all the way up to xn times yn summed up. So that's just a constant times 2 minus 2. That's then the coefficient in front of this n. So it's just some hideous coefficient in front of an m, but it's actually just a linear term in m there, so it's not that complicated. Next, here we have this bit. So c is another variable, so we'll pull that out. So we'll get minus 2c sum yi. So again, same thing I've done there. I've pulled the c out because it's not being summed. Then we've got plus m squared xi squared. So again, we'll pull out the m squared. So we've got plus m squared sum over xi squared. Then we'll pull out the 2mc sum over xi. And now finally we've got c squared summed from I is equal to 1 to n. So that will just mean adding c squared to c squared to c squared n times. So it'll just come out as n times c squared, where n is the number of data points we initially had. So hopefully I haven't made a mistake there. And now what we have here is a constant term. Then we have some linear terms in m and c. Then we have some squared terms. We have an m squared term, we have a c squared term, and then we have a mixed term where we have an m and a c. So this is actually just a multivariable second degree polynomial in m and c. So it's a two variable second degree polynomial function that we've got that is always going to be non-negative. Now some more intuition about it. Let's think about what will happen as you let m get bigger and bigger, or as you let c get bigger and bigger. Well, remember what it means, where it came from. If you let m be some absurd number, you let it get bigger and bigger, you can hopefully appreciate that the answer to this sum of all these square differences is going to become absurd. It's going to become bigger and bigger and bigger. If you're making m bigger and bigger and bigger, that's going to make your line at some point an absurd approximation for these data points. So the differences between the data points and your line is going to get absurdly out of control as well. So actually, as m goes off to infinity here, this s is also going to go off to infinity. The same with c. If you make the y-intercept get bigger and bigger and bigger, you're just making it absurd to the point that it's an absurd approximation. So of course, these differences are going to become huge. So again, it's going to go off to infinity. And the same when m goes off to negative infinity. We're talking about using steeper and steeper lines going down here as approximations. Again, it will become absurd and the differences will go out of control. So it's going to go up here. And the same with when c goes off to negative infinity. That's taking it down right down here. Again, absurdness. You'll end up with huge differences. So actually, our function is going to look something like, and I hate drawing 3D graphs, but I'm committed to doing it now, so we'll carry on. It's going to look something like this. The point I'm trying to get across is that it goes off up here, it goes off up here, it goes off up here. So we now want some minimum that's somewhere over here, or unfortunately on my picture I've drawn it actually at the origin, which is just typical that I've done a bad drawing. It's not in general going to be there, but it's going to be somewhere in this central part here. And basic facts from multivariable calculus is wherever that minimum is, so wherever, and since on my picture it is at the origin, I'm going to just use that. In our general case, it's not going to be at the origin, but just for the basis of the picture, here we go. There is going to be some minimum. Our function is just a two variable second degree polynomial, so it's differentiable everywhere, infinitely differentiable everywhere. So it's one of these perfect calculus functions. So wherever the true minimum of this function is, it's going to be a place where the tangent plane to the surface is going to be the level plane, i.e. it's not slanted at all. Its gradient is 0 in both the m direction, the x direction, and the c direction, the y direction. So it's going to be the place where the tangent is this level plane because anywhere where the tangent isn't the level plane will have a direction where if you go in it, you'll go down. You know, if the tangent wasn't a level plane, if it instead was at some sort of angle, then that couldn't possibly be a minimum, because if you went in this direction, you would be going down, so it wouldn't be a minimum. The minimum has to be the turning point where the tangent plane is turning from being oriented one direction. So in this case, it would be oriented in this direction, where it's now turning to being oriented in this direction, and in between those two, it has to go level for a moment. So at the minimum, the tangent plane is going to be a level plane, and therefore the partial derivatives of this function have to both go to 0. So and I don't want s. So the partial derivative of s with respect to m is going to need to equal 0, and the partial derivative of s with respect to c is also going to need to equal 0 at the minimum. And the wonderful, brilliant thing about this is that there's only one place for this function where this happens. There's only one solution to this. If there were more solutions, if there were multiple places where the curve had the tangent plane being level, then we'd be in trouble. We'd have to actually then wonder which one is the real minimum. But there's only one answer in this case. That's why this function is beautiful, because it's only second degree. There's only one place where this is true, and therefore that has to be the minimum, because at a minimum this has to be true, and since there's only one place for this function where this is true, we can conclude that that place is the minimum. So we just now need to work out where is that point where this is true. We'll see how there's only one solution to it, and that will then be our solution for what is the minimum. So let's find these derivatives then. So we'll start with the partial derivative with respect to m. So that first term, sum of yi squared, that is just a constant, so that will go to 0. The next term we have a linear term in m, so when we partially differentiate that, we'll just get its coefficient. So the partial derivative of s with respect to m, the first part is minus 2, the sum of, I'm going to write it the other way around, xi, yi. Then that next bit here, that is a linear term in c, so that's fine. That will go to 0 as far as the partial derivative with respect to m is concerned, because it's a constant as far as that partial derivative is concerned. Then we've got a quadratic term in m squared, so that's going to differentiate to plus 2m times the coefficient. So plus 2m times the sum of xi squared. Next, we have this term here, so that the mixed term. So the c is just a constant as far as the partial derivative with respect to m is concerned. So this is a linear term in m, so it's going to become just the coefficient of the m. So they'll become plus 2c times the sum of xi. And then finally, the nc squared, as far as the partial derivative with respect to m is concerned, that's a constant, so we don't need to worry about that. So there's the partial derivative with respect to m. Let's now do the partial derivative with respect to c. So again, that first thing is just a constant, so that's gone. The next term, the minus 2m, the sum of yi xi, that's only a term in m. So as far as the partial derivative with respect to c is concerned, that's a constant, so that goes. Next, we have a linear term in c, so that will become just the coefficient, so minus 2, the sum of yi. The quadratic term in m squared is a constant as far as the partial derivative with respect to c is concerned, so that's gone. And then we've got plus 2, and then we'll get 2m, the sum of xi, because again, the m is a constant. We view the m as a constant as far as the partial derivative is concerned, so it's just a linear term in c. And then we've got our quadratic term, which will go to 2nc. So those are our partial derivatives, and we now want to find where they are both equal to 0. And this is the reason there's only one solution to this, because even though these things look hideously complicated, the hideously complicated bits are these sums, which are just constants. So actually we've got a constant here, plus 2m times a constant, so a linear term in m, plus a linear term in c, and it's the same here. We've got a constant plus a linear term in m and a linear term in c. So we've actually just got two simultaneous equations, the linear equations. So we've got two linear equations in two variables. Linear algebra now, they're just simultaneous equations. There's only going to be one solution to that in general, as long as they're not parallel. And you can see from these coefficients that we've got here that they're hopefully not going to be parallel. Indeed, they're not parallel. We do get one solution from this system. But as far as linear algebra is concerned, as long as the two lines that we have here are not parallel, then they will meet at just one point. So there's only going to be, in general, one solution to a system of two linear equations in two variables. So let's now go ahead and solve them. So the way I'm going to do this is I'm going to rearrange this one to get c is equal to an expression involving m, and then I'll substitute it in here for c, and then we'll just have an equation in m, and we can rearrange for m is equal to, and then we'll just plug that m is equal to back into our expression for c to get what c is equal to. And we're going to get some beautiful formulae, which are the least squares formulae for what the m and the c need to be in terms of our xi and yi. So let's do this. So firstly we'll cancel the 2 from here. So we're cancelling that 2, and that 2. So we're just multiplying everything through by half, which is a perfectly valid algebraic manoeuvre. Next, what we're going to do is we're going to take this onto this side and this onto this side, and then we're going to divide through by the n. So we'll get that c is equal to, so we'll have the sum of the yi's minus m times the sum of the xi's, and then all of that divided by n. Now what I want to do is substitute that in here. Again, I'm going to get rid of those 2's. So that 2, and that 2 have had their day. They're off. So we're multiplying everything through by half first. And now we're going to substitute in the c. And we'll get that minus the sum of xi, yi plus 2m the sum of xi squared plus, and I've managed to put a 2 in there, so get rid of that 2, plus the 2 has gone, so sum of xi times the sum of yi minus m the sum of xi over n is equal to 0. Now, did not mean to do that. Come back down. So we now want to rearrange to get m is equal to something. So we've got a constant term here, so we'll take this to this side. We've also got a constant term that comes out here, so we'll take that onto that side as well. So let's do this. So we've got m times the sum of xi squared, that's fine. We're then going to have a minus m times the sum of xi all squared, which of course is not the same thing as the sum of the xi squareds, divided by n. And then on this side we're going to have is equal to sum of xi yi, and then we want this thing on this side, so minus sum of xi times the sum of yi, which again is not the same thing as this, divided by n. So we'll have minus sum of xi, sum of yi, divided by n. Good. So we can now factor out this m, and we'll have m of sum of xi squared minus 1 over n times the sum of xi squared is equal to the same thing as we've got there. And so we'll just divide through by that. So we'll have m is equal to sum of xi yi minus 1 over n times the sum of xi, whoops, almost made a mistake there, sum of yi divided by, and then that will be divided by the sum of xi squared minus 1 over n sum of xi squared. And then we can just multiply top and bottom by n to get this in the more conventional form that it's presented in. So m is now equal to n times the sum of xi yi minus the sum of xi sum of yi divided by n times the sum of xi squared minus the sum of xi squared. And I suppose if I wanted to write it beautifully, I would actually now finally agree to actually write out the I is equal to 1 to n again. So sum from I is equal to 1 to n of xi yi minus sum from I is equal to 1 to n of xi times the sum from I is equal to 1 to n of yi. This is the reason I haven't been doing it for the entire video. Divided by n times the sum from I is equal to 1 to n of xi squared minus sum from I is equal to 1 to n of xi all squared. So there is your final formula for what m is equal to. In fact, I wish I hadn't bothered writing that one out because this one is far prettier. So given all these data points, the xi and the yi's, you're given those at the start, you can, in principle, do this horrific calculation. You can work out what the sum of xi, yi is, you can work out what the sum of xi is, you can work out what the sum of the yi's is, and you can work out what the sum of xi squared is. And if you work all of those things out, you can plug them into this formula, and you will get out the value that you need to make m in your line for it to be the least square best fit, which will be an arguably good way of defining what best fit is. So isn't that beautiful? We just have one final thing to do, which is to now stick this back into our equation for C. So you can just about get them on the same piece of paper. So here is our expression for C up here. So we need to just stick this into this. It doesn't look great, but we're going to have to do it. So how am I going to get them both visible? We'll go like that. So we're doing this here. C is equal to 1 over n times the sum of yi minus 1 over n the sum of xi times this hideous thing that we've got for m, which is sum of xi yi. And I'm copying the wrong one out. Well, we can put it back. Since I've started now, we'll go back and put it like this. Or will I regret that? I probably will regret this, but never mind, we'll do it. We can multiply through by n next to make it correct. Xi yi divided by sum of xi squared. If I'm going to make a mistake now, this is the bit where I'm going to make a mistake. Excellent. I think that's perfect. Let's just check it. We have copied in this one here, and it looks absolutely fine, so good. So now, let's try and manipulate this a bit. So we need to, firstly, so we need to combine them, get them over the same fraction somehow. So let's write this out here. C is equal to, I'm actually going to write it back like this way, and then we'll have multiplying out. We've got a fraction here multiplied by a fraction, so it'll become minus sum of xi times the sum of xi yi plus 1 over n times the sum of xi squared sum of yi divided by, and then it'll be n times the denominator, sum of xi squared minus 1 over n times the sum of xi all squared. So this is looking truly hideous, but it is going to simplify, I'm confident of that. Let's just make sure that I have not made a mistake here. So we've taken this thing and we've multiplied it by this thing. So we've got a minus sign there, then we've got this bit, and then we've made this plus, which is not the right thing to have done. Not the way I've written it, because I've written the minus sign out the front here. If I put this, I suppose I can swallow the minus sign inside, but at the moment this is written in incorrect form. So I'll turn that back into a minus and we'll have brackets around there. Gosh. So let's multiply top and bottom here by this thing so that we've got them both over the same denominator. So multiplying out, we'll have sum of yi times the sum of xi squared minus 1 over n times the sum of the yi, sum of the xi squared. And now let's get this minus sign right this time. So it'll be minus sum of xi yi. And now the two minus signs will cancel, so it'll be plus 1 over n sum of xi squared. And now I know I've done it right because it's going to cancel with that other one there. So that's reassuring. And then all of this will be divided by our denominator, which is n times. And let's multiply that n out now. So it'll be n times the sum of xi squared minus sum of xi all squared. And so this is actually going quite well. So this hideous thing here is the same as this hideous thing here, except for a minus sign. So those beautifully cancel with each other. And now what we're left with is that c is equal to the sum of yi sum of xi squared minus the sum of xi times the sum of xi yi divided by n times the sum of xi squared minus the sum of xi squared. So there we go. Those are our two formulae. I'll now put boxes around these. So here is the one for C. So you give me those xi's and those yi's. You can work out all of these. It's not a pretty computation, but you can work out the sum of all the yi's. You can work out the sum of all the xi squareds. You can work out the sum of all the xi times the yi and the sum of xi. So you can work all of these things out, stick them into that formula, and you'll get your C value. And then we've got our M formula over here, which I'll circle in yellow as well, the prettier one without the I is equal to 1 to n in. So again, you can work all these things out and you can stick them in and you will get an n value out. And then you can put those together into the y is equal to mx plus c format, and you'll then have the equation for your least squares best fit line. And that will be an intuitively reasonably good best fit for those points. So thank you for watching this video. I hope that you have understood the derivation that we've been through here. For the love of God, do not try and memorize these formulae. Understand the derivation, how we got them, and then if you ever do come across a situation in real life where you do need to actually do this, you can derive them again and actually perform the computation. Thank you for watching.